we are going to continue talking about the separation science, this part. So we're going to finish this slide. I think so. We're going to finish this part and move on to UPLC. And then so if we can even finish UPLC, and we can talk a little bit more about ion chromatography. Okay, so now we can start. Yeah. So for last week, we already talked about what? We already talked about so how we can play with the K value, right? Okay, and then we talk about once the K value is okay, once you get K equal to 10 for the last compound, and then even some compounds still not well separated. And then so how can we improve the alpha, the separation factor? And then so for that one, so we start talking about, say, the solvent selectivity triangle, right? Okay, so this solvent selective triangle, and then so we use this example to show, like, for reverse phase, and then so we can use water to adjust that, and then so we add different organic modifier. The normal one is ACN, methanol, and also THF, and then so you play with that. So here again, I say just using isochromatic, but later on when you're using the solvent program, so still is same concept. Okay, and then after that, we start talking about using one example, which is Metcon green. So, and about the separation. And for Metcon green, this one really illustrates a very good example to have a good practice. So, starting from the chemical structure to think about how we can do the analysis. Okay, so we did that practice together. And then so I hope that gives you some idea about what kind of chemical property we have to think about while thinking about the separation or sample preparation technique. And then for the sample extraction, and for this one particularly mentioned about acidic buffer and antioxidant and so on. And then so for the sample cleanup and so on. Okay, so that is for last week we talked about those things. And then we move on to talk about other kinds of partition chromatography, not just reverse phase and normal phase. And the first one we talk about is the ion pairing chromatography. Well, we say that it has plenty of problems. Okay, like we already talking about here. Let me say in reverse phase column. So reverse phase, the stationary phase is relatively nonpolar, and then so like C8 or C18, and the mobile phase is kind of polar, right? Okay, so and however, so this one, so that's why it cannot really retain polar or ionic compound. It's really good for those relatively non-polar compound, less polar compound. So if we have polar ionic compound, so they will just elute at or near the dead volume. So that's why. So if we really want to use reverse phase chromatography to do the separation of very polar ionic compounds, so then you have to either to derivatize your analyte. So to add some hydrophobic tail to the analyte to make it less polar, or what you can do is, like, say, we mentioned like do some air pairing. So, but in the air pairing chromatography, we already see that it's really time consuming. And then so when you add the chromatography, have to add the air pairing reagent. And then so that agent normally is quite harmful to the silica column. And then you have to wait for the equilibrium of the air pairing system, which is relatively slow. And then so and many of the limitations. So that's why so this is not really favored. And then the question is, like, then if we really want to deal with polar compound, so ionic compound, what can we do? You say you have normal phase, right? Yeah, for normal phase we can separate those polar compounds. But if I say even we can include some ionic things, so can we do that? Well, anyway, so because of that, so this development of the partition chromatography, it become the hydrophilic interaction liquid chromatography, which is particularly designed for the retention and separation of very polar and ionic compound. Okay, so and this is what we stopped last week. We say again, so when we talk about making the stationary phase, same for helic, you also start from the silicon color, and the silicon color is like standard organosilicization chemistry used to modify the surface silicon to convert that OH to derive it to have a long tail. And then we say that, say here, so and for normal phase chromatography, when you want to make it to be polar, the stationary phase, so the R functional group, so R group is normally cyano or amino or diol, okay? So, and then this compound, so the functional group, the R functional group, they make it polar, make it stationary polar, and they make them have the ability to retain those hydrophilic compounds, okay? So, and then you may want to ask the question is to say, well, since you already have this one, why are you still using helic? And then that'll be the same thing, right? So, and what is the difference of the stationary phase of helic and normal phase? They all retain polar, but how can we know which one I can use? And then, so which one is better to use in which situation? So, well, for helic, the R, this functional group, the stationary phase, is quite hydrophilic and quite often charged. So it can be positive charge or negative charge or even like twitter-ionic. That means like it includes both positive ion and also negative ion on the stationary phase. Okay, so and then overall it's neutral. Okay, so and for helic, because it's actually retain polar compound, so we can consider it as a variation of normal phase chromatography. But we should know that so the stationary phase is hydrophilic for helic. It's hydrophilic. Okay, so this one hydrophilic interaction liquid chromatography. So this one means like stationary phase hydrophilic. So which is more polar actually than the normal phase. And then so typical eluent for helic consists of 40 to 97% of ACN in water, or and also can include volatile buffer. We look at this one. What kind of reminds you? This is kind of the mobile phase for what kind of chromatography? ACN in water. You look at this one, I think, oh, that is the mobile phase used for reverse phase. Huh. You said this is a variation of normal phase chromatography, but why use like say a mobile phase that is quite similar to the reverse phase? So that is good thing for helic actually. So that is very good thing for helic. So helic, because its stationary phase is quite hydrophilic and quite often charged, and also it has a water enriched layer which established within the stationary phase. So that's why it's able to deal with a mobile phase that is water with organic solvent, and particularly you see that it can use a quite high percentage of ACN in water, can go up to 97%. So, but here you should keep something in mind is at least 3% of water is needed. So ACN should not be more than 97% because the helic stationary phase, so it's hydrophilic, it has to contain at least 3% of water to maintain the hydration of stationary phase. Okay? So that make it, although it's stationary phase polar, but now look at its mobile phase, make it to be different from the traditional normal phase chromatography, right? So because we know that for traditional normal phase chromatography, what is the mobile phase? What is the mobile phase? The mobile phase of normal phase chromatography is what? Hexane, the nonpolar, right? The hexane, so they are methylene chloride, chloroform, alkyl ether, right? So those compounds, do you think the mobile phase is really good to wash out those really polar compounds? No, because the mobile phase, like say, it's not really that polar, it's really non-polar. And for very polar compound, if we stick to the stationary phase, this mobile phase is really difficult to really wash them out, right? And also, they're not easily so ionized because they're not polar, the mobile phase. They're not easily say ionized in ESI, so it's not really a good choice if it connects to the mass detection. But how about helic? Look, non-mobile phase ACN, water, and also can be volatile buffer. What is volatile buffer? The volatile buffer means that they can, so those normally is formate or acetate, okay? So can be the formate or acetate we mentioned about the buffer before. Can we use phosphate buffer here? Can we use phosphate buffer here? Yes or no? Can I use phosphate buffer here? Remember we mentioned that the different buffer last week. So how about those phosphate buffer you usually use? So HPLC, no, very good, thank you. No, because it's not really volatile, okay? So it's not really good for when you're using the LC system to connect with mass spectrometer. Okay, so we use formate, so acetate or formic acid, acetic acid. So they're good too, okay? So like formic, oops, sorry, right here. So formic acid or acetic acid. So they're good too. So those buffer, they have very good solubility, even in high concentration of organic solvents. So that means perfect buffer for the Helic mobile phase. Okay, so and then so therefore Helic is a very mass-friendly technique. Why? Several things. Okay, one thing is because it has very high level, can be high fraction of ACN. Okay, so that makes it ACN is more easy to evaporate, and then so in ESI can really help to increase the ionization efficiency in the ESI. Okay, and also it contains the volatile buffer that also increase the ionization efficiency. So in ESI, so that's why so Helic is a very mass-friendly technique, and by changing the technique from reverse phase liquid chromatography to Helic, so it can increase the sensitivity by 10 to 1,000-fold. So for those hydrophilic analyte, so because of that, we can see the polar compound, so they can show good solubility. So in this kind of mobile phase, so and which overcome the poor solubility like you often encountered in normal phase chromatography because it uses very long polar mobile phase. So for those really hydrophilic analyte, so they actually have very poor solubility in the mobile phase of MPC. So, but now because for Helic, so it uses ACN in water with some buffer, and then that makes it quite friendly or quite good mobile phase. So for those hydrophilic analyte, because they have very good solubility in this mobile phase. Okay, so and therefore, so because of this one, so the Helic have even handle ions. So so those very hydrophilic compound, and then so such as so those carbohydrates, acid and base, you see shown here. So amine and charged ones, you see that. So I think organic charged ones, organic or inorganic ions, amino acids, protein digest, and so on. Okay. So, and I have one question. So here, so now you see the mobile phase can be 40 to 97% of ACN. So if the ACN percentage increase in the mobile phase, so does that increase K retention factor or decrease K in Helic? You can answer that in chat box. Increase or decrease the retention factor of the polar compound in Helic. If we increase the ACN percentage, okay, so increase ACN from 40% to 90%. So does that increase the K value or decrease the K value of polar compound? Any idea? So actually, you see, because now we're dealing with polar compound, right? So water and ACN, which one is more easily wash them out? For polar compound, for hydrophilic analyte. So water is more polar. Water actually can more even easily wash them out, right? So that's why. So in Helic chromatography, when we change to a higher fraction level, high level of the organic solvent, so the retention actually increase, right? Okay, because ACN compared with water less polar, right? Okay, so it's not really say if we're using higher fraction of ACN, so and then so will be less elution strengths. Okay, so and then the retention actually increase. Then you will see that. So that's why. So when we talk about the mobile phase, also we have solvent A and solvent B. Now the solvent A is different from the solvent A we talk about in reverse phase. So let's look at how does Hilliard work. As I just mentioned, the stationary phase is hydrophilic and quite often also charged, can be either negative or positive or neutral. So this treated ionic stationary phase, as you can see here. So this is schematic illustration of the stationary phase of a treated ionic stationary phase. ZIC means treated ionic station phase. So why is it treated ionic? That means it has both negative charge and positive charge here, as you can see here. So this one is positive charge, negative charge. So that's why. So overall is neutral. Okay. So under a Hilliard condition, a water enriched the liquid layer. So that's why you can see water here, right? Okay. Water enriched liquid layer will be established. So within the stationary phase. So we just mentioned that we need at least 3% of water to do what? To keep this stationary phase hydrated, okay? So then that's why you can see this polar is water here and hydrophilic here, okay? And also it has ionic site here. So the separation is achieved not just by one single mechanism, okay? So it's separation based on, can be achieved by first, the partition of this polar analyte from the eluent into this hydrophilic environment. Okay, so what kind of interaction can be for station phase? It can be separate based on, so this type interaction include the hydrogen bonding, right? Okay, the hydrogen bonding. And also it include what? So also include some dipole-dipole interactions, right? So therefore, both hydrogen bonding, the extent of which depends on the acidity or basicity of the analyte, right? Okay, and the dipole-dipole interaction, so which depends on the dipole moment and polarizability of analyte, so are factors so that governs this kind of the retention, okay, from this kind of the retention in this hydrophilic environment. Don't forget, we also have the charge site. Okay, so the separation can be also achieved by these electrostatic interactions. So if the analyte so can be charged, okay, so and then so we're going to have this electrostatic interaction separation as well. Okay, so and therefore the combination of these two mechanisms result enhanced polar retention. Okay, not only just the organic polar compound, but also some ionic compound as well, as you just see so in previous slide. Okay, so separation achieved by the combination of two mechanisms. So it can be including both the electrostatic interaction, so particularly for those ions, and also partition of the polar analyte, so from the mobile phase into the hydrophilic environment. And in this mechanism, so the first one, this one, so both hydrogen bonding and dipole-dipole interaction. So dipole-dipole interaction are the factors that govern this kind of separation. Okay, retention. Okay, so if you look at the characteristic of Hilliard, so we can say Hilliard is opposite to reverse phase, because then for Hilliard it's polar, so the polar compound so will retain, and then the least polar compound comes the first. Okay, but reverse phase, the least polar compound, it just takes retained, and the polar compound cannot be retained. So the elution order can be, if we talk about that, it would be quite totally different. And then so the higher organic solvent in the eluent can increase the retention of the solute, right? Because for polar compound here, if you want to really wash the polar compound out, you want the mobile to be polar. But of course, obviously, so if we have 40% ACN, if I say they have like 60% water, 40% ACN, and 60% water. So, and this one is definitely have a stronger elution power than those contain 90% ACN, right? And 10% water, right? Okay, so it's different scenarios. So that's why I talk about that one. Okay, so I hope you understand. And then and suitable buffer for helic are ammonium salts of acetate or formate. So that means ammonium acetate or ammonium formate. But also formic acid and acetic acids are recommended, all because of their excellent solubility even in very high concentrations of this organic solvent. And if we already talk about that, you already see the helic can retain highly polar and light. So that could be unretained by the reverse phase chromatography. Actually, helic shares different things, several different aspects with different kinds of chromatography. If we say this is a helic, so what is the common thing between helic and reverse phase chromatography? If it's reverse phase chromatography, they have pretty similar mobile phase, right? Okay, so ACN, water, some buffer, right? So, and how about the common things between helic and IC, ion chromatography? So they both can handle ions, right? Okay, some of the compound. And how about helic and normal phase chromatography? And then so they are pretty common, have some common things like in stationary phase, they could be very polar, right? Polar stationary phase. So this is so helic is just like something pretty interesting. So it's complementary selectivity to reverse phase chromatography, because reverse phase handle those hydrophobic things and helic handle this hydrophilic, more polar ionic species. And you can see because of this mobile phase, and so it can enhance the sensitivity mass spectrometer, because it can use high organic fraction and also the volatile buffer, which promotes ionization efficiency in ESI. So that's the reason for that. Okay. And for helic, it shortened the sample preparation procedure. Because for the solid phase extraction, so for sample cleanup using SPE, protein precipitation or liquid extraction step usually involved. So involve organic solvent. So, and if you use the reverse phase, so you may have to evaporate the organic solvent and reconstitute so the sample in the mobile phase before injecting into HPLC. So like because normally in HPLC, in reverse phase chromatography, we start with higher level of mobile phase A, right? Solvent A. Solvent A is normally say aqueous phase. So a high fraction of aqueous phase. So by using helic, so anyway, so it uses very high fraction of the organic solvent. So there's no need to eliminate to do that evaporation. You can just skip that and by direct injection. Okay. Well, okay, so for the helic, we're going to use another example. We are going to talk about the analysis of melamine in food. So anyway, so again, for this one, I just want you guys to look at the structure, and we started from structure again. And then so we kind of started from chemical structure and thinking about, so why, so we have to use this kind of column, why we have to use this kind of separation or sample cleanup technique. Okay, so again, so first let's look at the structure of melamine. So this is the melamine, and then when you look at this structure, what calls your attention? N. How many N? 6N, okay? So C3H6N6. So it has a very high fraction of nitrogen, so in its mass. So actually nitrogen contributes 66% of the mass. Okay, so melamine occurs also because it's So amine here. So it's a weak base. It's a weak base. So and this basic ionization constant is about I think it's about 10 to minus 9. So that's why. So it's kind of like when pH is less than 4 and then smaller than 4. So when it's acidic, it can make it so protonated. So protonated, that means this one add on. Okay, can make it with this one. Okay, understand? Okay. So if its pH is less than 4, acidic. But it's normally neutral if its pH range is 6 to 13, like that one. And if you look at this structure, so you can see the water solubility of this one is pretty good. And how about the MRL, which is the minimum reporting levels? So it's normally talking about the toxicity issue. And if we look at this one, probably we look at LD50 first. So LD50 is the parameter often used when we talk about toxicity. It means the median lethal dose. That means the dose required to kill half of the members of a tested population after specified test duration. So basically, if we have much smaller LD50, that means more toxic. The smaller the LD50 number, the more toxic this compound is. But if you look at this LD50 number, so for melamine itself, it's just a 6 gram per kilogram of body weight. Is that really toxic? I just give you some reference. You know TCDD, right? This is kind of very toxic dioxin. So the most toxic one. So its LD50 of TCDD is 10 to the minus 6 gram per kg. How about DDT? You guys know that, right? Okay, the pesticide is 0.1 gram per kg. But this one is 6 gram per kg. That means it's not really toxic. It's comparable to table salt. But why we care about it? Okay, so we'll see that. Why we care about it? Because melamine has been added into the food, into dairy, into baby formula, so into pet food, in human food, to mimic what? To falsely represent protein level. The reason for that is because the global standard method to measure the protein content in food, they use some Jadel method. So that Jadel method cannot differentiate. So whether the nitrogen is from protein or something else. So it just measures the total amount of nitrogen. What you can do is that first you do just the acid, boiling it, a very strong acid, sulfuric acid, to convert all this nitrogen into the ammonium sulfate. And then once for ammonium sulfate, and it has sodium hydroxide as strong base to release that ammonium already get from the protein, if it's protein, okay, to ammonium gas, and then use boric acid to catch that ammonium gas to make that ammonium ion again, and then back titration the boric acid to see how much boric acid have been used to capture this ammonium gas, and then it can know the molar concentration, the moles or the mass of the ammonium. So they know that. Okay, but the limitation for that one is cannot differentiate. So whether the nitrogen is really from protein or not. So if you add melamine, same. It can be just like say react with sulfuric acid to become ammonium sulfate, and then have all this one. So that's why. So people just like say very bad people just add into food to mimic the protein. Well, and because it's has different toxicity issue, but not really say its own toxicity. It has because of other reason. Okay, so we'll talk about that very soon. And then the minimum reporting level, that means requirement for its concentration in food. So this is the US FDA. So they have 3 different commodity-based MRL. So they can see for pet food, MRL is 10 microgram per gram. For human food, it's 2.5 microgram per gram. For infant food, it's 1 microgram per gram. So why? the MRL level is the lowest for infant formula. Why is that? It's because infants, they mainly rely on formula as the food source, right? Okay, so they're babies, they have no other food. So that's why. And so this is, they need to take that one so as a main food source. And also the renal system, they're not really fully developed. So that's the reason for that. Okay. So therefore it set the daily tolerable intake. So and that is for child will be less. Okay. So we have more strict level. So melamine actually is industrial compound. So it's not really food additive, legal food additive. It's just an industrial compound used for plastic. So to production of this polymer resin, and also it used in fertilizer to control the rate for nitrogen seep into the soil. And then so it produced those durable semi-heat resistant plastic. So used that in table wells. So and when table well tested, it found that melamine only leach out at prolonged high temperatures and acidic conditions. So that means, like say, you only say when you really hit it, so at very high temperature for on the acidic condition, and then melamine comes out. So well, and what the problem actually caused by melamine? So because the melamine we added is not just by itself, so it has side products get in as well. And the two that really cause trouble is melamine and cyanuric acid. Melamine and cyanuric acid. But let's look at the difference of this melamine, amylide, and cyanuric acid. For melamine here, amine, three amine groups, right? Okay. So, and then for this one, have one amine group replaced. So this one actually, we can write it in this way. So it can be, open this one. Oops, sorry. And we can have OH here. So, and then, so here's N. So double bond, right? Okay. So, and then, and so this way. So, I mean, this part can rewrite as this. So it's actually one amine group replaced by OH. So here can be two amine group replaced by OH group. And then, so that's why cyanuric acid is three amine group replaced by OH group. Okay. So what problem for this two? Because when melamine and cyanuric acid, when they are together, so they can form some jigsaw puzzle-like two-dimensional hydrogen bonding network. The nitrogen, hydrogen, oxygen. So they have this kind of highly organized, so lattice crystal structure. So, and what happened to that? Let's look at the solubility. So because for melamine itself, its solubility is 3.24. But once it formed this crystal structure with cyanuric acid, this melamine cyanurate, it has a much smaller solubility. Okay, so you can see the solubility actually dropped to 0.01 gram per liter. And then that caused a problem because it's much less soluble in water. So, and it has toxicity higher than that. And then it becomes much less soluble. So that's why. So when they are absorbed into the bloodstream, they concentrate. And then so they've crystallized and form a large number of those round yellow crystal. And then so those one then block the and damage the renal cells that line the tubes, causing the kidney to malfunction. So that's the reason. So it's melamine together with cyanuric acid. They form very insoluble melamine cyanurate crystal, and then which can block this renal microtubes and then cause the kidney to malfunction. So that's the reason. So that's why. So obviously, so when we are measuring the melamine in food, we're not just looking at melamine. At the same time, so you also want to measure cyanuric acid as well. Okay, so we normally see people also do both of them. So when we do this analysis, you'll encounter different sample matrix, like the milk powder, dairy products, the chicken, fish, and so on. So, and when you take the sample, you have to make sure you take the representative sample. And extraction normally just vertex or sonication. So not really for GCMS, can think about this one. So, and you can see that in one of the methods, it even add a little bit dialpha amine. So for this one, this is pretty tricky. Why? Because look at this one. So there are four, actually three side products of melamine. So altogether we have 4 compounds. But for this two, so the amyline and amylite, they shows extreme low solubility in just traditional extraction solvent, like it's very low solubility in ACN or just water. So that's one. So, and also this one, so the melamine and cyanuric acid, they form this one, the hydrogen bonding crystal, right? Okay. So, and this crystal also is pretty hard to dissolve. And people found that with a small fraction of dialpha-amine added into the extraction solvent, so this can really help. So the extraction and dissolution of all 4 melamine-related compounds. So from a variety of matrix, and also it can say help to even dissolve the melamine and cyanuric that crystal. Okay, so this is in some of the paper and reference, you see the addition of the dialpha-amine in that. And in most of the, however, in the LCMS method, they just directly use in the ACM, but however, they acidify with some hydrogen chloride. Okay, so and after extraction, sample normally washed by DCM for several times. The reason for that is get rid of those less polar, so lipid and those things, okay, fat. And then then the run the aqueous extract, so through SP cartridge. And think about what kind of cartridge we can use. Here, even it mentioned MCX, but does MCX then works for all 4 compounds? Keep that as a question. Okay, and then so what kind of instrument we can use? LCMS definitely is a good choice. We're talking about LC, and then we give the example here, right? So how about GC? If we want to use GCMS, not really good because of this compound amine. You can see, you call that, see, NH2. We call this H active hydrogen. OH. We call this H active hydrogen. So they make it 2 polar to run in GCMS. So if we really want to analyze that in GCMS, you have to replace this active hydrogen so by some less polar functional group. So we do chemical deratation to convert that, okay? So to deactivate it, and then to derivatize it, and then it can be analyzed by GCMS. So that means if you do use GCMS, you have to have prior chemical derivatization. That'll be extra step. Okay. So, however, if we do the LCMS, there's no need for chemical derivatization. So now let's look at the sample cleanup procedure. For this 4 compound, if I say I will focus on these 2, melamine and cyanuric acid. So I have 2 different kinds of here first you want to answer this question. What is SCX? What is SAX? Strong cation exchanger. So C means strong cation. Okay, we actually already mentioned that in Melanocortin green. Strong anion exchanger. Okay, so that means they can retain cation, retain anion. So can you tell me if it's A, if it's B? Okay, A is strong cation exchanger, B is strong anion exchanger. Now I want to clean up. So the sample, I want to retain melamine and cyanuric acid. The first question is, do I use the same SPE column to do the sample cleanup for melamine and cyanuric acid? Yes or no? do I use the same SPE cartridge to do the sample cleanup for melamine and cyanuric acid? Yes or no? Do you want to answer the question in the chat room? Can I use the same? The answer is no. Very good. Thank you for the answer. Very good. So, and then the next question. So if I want to do the sample cleanup, for cyanuric acid, so which SPE column I can use? A, SCX, B, SAX, A or B? Now I'm talking about cyanuric acid. A or B? Do you want to answer? A or B? B, very good. Thank you. Why? Why is B? Why is B? Look at this one. Now it has three OH group here, right? OH group here. So for this one, it's more easily what? To lose the hydrogen and to be negative charged, right? Okay, so that means after we treat the sample, if you want to analyze, if you want to achieve enough sensitivity for both melamine and cyanuric acid, you might, after all the sample extraction things, before you go through the column, you may want to separate them into two halves. One half goes through SAX. The other half goes through what? SCX, right? So, and then there will be different things. If you want to make melamine to be charged, if you want to make melamine, because before we load the sample onto the strong kind exchanger, you want it to be charged. So if you want melamine to be charged, this one, so do you first need to what? Acidify it or make it add base to it? Okay, do you want first to acidify it, add acid to it, or to the sample, or do you want to add base to the sample before you run through the column, you run through the cartridge for melamine? For melamine, of course, you want to acidify it, right? So first, before you load the sample, you want to make it to be charged, right? Okay. So why this amine is easy to get protonated? Because it has known pair of electrons, right? Okay, so that's why. So you want to acidify it, and then you load on strong kind exchanger, and then you elute it with basic methanol, right? To break that interaction, and then do so. And for SAX, it's opposite, because you want to make this one to be what? To be negative charged. It's weak acid. So first you want to add base into it, okay? So let it to be negative charged, and then you load on SX, and then you use acidified methanol for the elution, okay? This is very important. You have to look at the chemical structure, and then you choose the right one to do the sample cleanup, okay? And then so for LC column, which one can use? If it's ions, some use ion exchange. So here, of course, we're using helic. So that's why we put it on example. But for mass detector, okay. So here, if we use ESI, so if I'm using cyanuric acid for analysis of cyanuric acid, do I use ESI positive? A is ESI positive, or B, ESI negative? Which one? For cyanuric acid. For cyanuric acid, we're going to use ESI negative mode or ESI positive mode. Negative mode, very good, thank you. Yeah, because then we'll make it negative charged, right? Okay, and then so, and ESI, we're using negative mode. But for melamine, we'll use which mode? Positive mode. Understand? Okay, so very good. Now let's see the standard method for the US FDA LC tandem MS method. The first one, so is add ACN water mixture 50-50 with acid hydrogen chloride, because make melamine charged. Okay, you know why is that? So it's why you use acid here. We play with, sometimes we play with acidity or pH while we do the extraction, because if for the amine compound and for the melamine, this one as amine, we often add acid while we do the extraction. The reason for that is because we want to make it charged, and then so more easily soluble, readily soluble, or easily extracted by polar solvent. Okay, so that's why. So with an SN and water mixture and with acid to make melamine charged and then more easily to extract it. And then so centrifuge and wash by DCM. And then so then we of course take the aqueous phase and extract the melamine by water and then go through the go through the strong contact exchanger. And then so blow dry, reconstitute into the initial condition here, and then so run through the Hillet column. Okay. So, and for this method, so the melamine has an average recovery of about 64%. So about the concentration range of 10 ppb to 500 ppb level. And then so it's already pretty good. So for sample cleanup, let's see. So for melamine, use one more of hydrogen chloride acid to ionize melamine in the sample extract. And then load the sample, so strong contact exchange, cartridge, and then using basic methanol for elution. Okay. But for strong ion, this one, we want to be negative. So that's why using 5% ammonium hydroxide, this base, okay, in water to ionize this one to be a negative charge, this to be positive charge. And then so you load on strong iodine cartridge, and then so use acidic methanol, which is 4% of formic acid in methanol for elution. I think now all of you already know why we have to use acidic methanol or acidic or basic methanol, not directly use the, say, acidic water. Why is that? Because later on, like for this one, if you want to reconstitute, blow dry and reconstitute the sample, okay, and methanol is much easier to blow dry than water. Understand? So that's why here, so we're using basic methanol or acidic methanol, because later on, if you have further treatment, if you need to pre-concentrate it, even not replace, and you want to like blow dry or blow that to much less volume, methanol is much easier to blow than under the nitrogen flow than water. Okay, so let's look at this fast US FDA LC 10 ms standard method. So, and this is also the method adopted by the government lab in Hong Kong. So, chemical testing lab in HKBU. So first you weigh 0.5 gram of sample into 5 milliliter centrifuge tube, and then you add 24 milliliter of this ACN water mixture. So with the acid here, right? Okay. So, and then this is not sonication, just vortex. So vortex is strongly mixed. So for 1 minute, and then centrifuge for 5 minutes at 4 degrees C. So this is the speed. And then transfer the 5 milliliter of superlatent. So the aqueous layer, right? Okay, so this one. So superlatent into the tube, and then add 5 milliliter of DCM into the tube and the vertex for 2 minutes, and then centrifuge that one and take the upper aqueous level. Why? DCM is heavier than water, okay? DCM, think about density of DCM, right? It's heavier than water. So that's why if we want to take the aqueous phase now, it's upper, because now using DCM to wash it, okay? Don't make a mistake in this step, okay? And then so we just add a few more water into DCM layer and re-extract it and repeat. And then so transfer the entire upper aqueous layer into the tube and combine with previous extract. And then so in this method, they even just like make up to 10 milliliter. But if your sample contain very trace level of melamine chloride, sorry, the melamine. So you may not want to like say make up to 10 milliliter. That's a lot of dilution. Okay. So, and then so you can see that centrifuge, filter that one. So it makes the dilution, and then filter the sample with the syringe filter, and then so put that into vial and also add the isotope labeled melamine. Okay, so it can be both nitrogen 15, carbon 13 labeled, or just like carbon 13 labeled. So this both of them quite popular. And then come to the HPLC condition. So let me see what time is it. Oh, okay. So pretty enough for 50 minutes. How about we take break for 5 minutes? So come back at 56. Okay. So now let's take a break now. Okay, so we start again. Yes. So I see this one. So, and we're using hidden column. So, and that's why we see for mobile phase A now is 5% of this volatile buffer and 95% of ACN. Now you can see now the phase A is not aqueous phase. The phase A is one contain, so high fraction of organic solvent. Okay, so it means, so it starts with low polarity organic phase, and then then switch to the phase B. Phase B contains 50% of water. So therefore, so this is more, say, polar. Now phase B more polar. Phase A is less polar. And then, so that's why it's begin with low polarity organic phase, phase A, and then switch to 50% of solvent A, 50% of B, and then back to 100% of mobile phase A again. So because here is increased to illusion of those more polar compounds. Okay, so and then the flow rate. But for the compound, we can see, so and for mass spectrometer using ESI, if it's for melamine, so for melamine using positive. But if you also want to analyze the cyanuric acid, you have to use negative mode. Okay, so for melamine, we see, so melamine, the precursor is 126 because the molecular weight 126. Okay, molecular weight is 126. So that's why a protonated is M plus 1. So precursor ion is 127. And then, so, and for this, like say, isotope labeled melamine depends on how many, so has been isotope labeled. And this one, so it's just molecular weight plus 6. So that's why 133. And this one plus 3. So this 130. Okay. And then, so melamine can can generate 2 pairs of mother and daughter ions. So it can be 127 to 85, 127 to 68. Okay, so 2 pairs of that. So if it's cyanuric acid, so cyanuric acid, because molecular weight, then cyanuric acid will be negative. Okay, so if it's we say cyanuric acid. Okay, I think to be consistent. But it looks like Chinese New Year because cyanuric is one. Cyanuric acid. Okay, so that'd be negative. And then, so you see that because the molecular weight is 129, so then will be M minus 1. So that will be 128, will be the precursor ion. And then, so they have the fragments, so, and become, say, yeah, so I think it's kind of 85, cannot remember, so this one. But anyway, for those tandem MS, so when you are using identification, so we see the individual selective reaction monitoring ion ratio in the sample should be like within plus minus 20% with respect to the authentic standard. We compare that ion ratio, so to the standard, and should be within that, so 25%. And then it shows the mass spectrometer of 1 ppb melamine standard. And then this is the carbon 13 labeled one. And then you can see, so this is signal to noise ratio. And for melamine 1 ppb, already pretty okay. So signal to noise ratio, you can clearly see that, right? Okay. And for 10 ppb, so spiked infant formula, also can see it. And then, so, and good linearity for that one. And then, so, and this is what to do. So sample clean up. Let me see, and condition that one with micellar water. And then, so, and this then acidify it, right? And then, so, that one, so elute that with, so, basic methanol. And then, so reconstitute this residue So in formic acid in ACN, and then do that. Okay, so this shows you, so this is without the sample cleanup, and this is with sample cleanup. So this is milk powder contain 1 ppm, 1 ppm. So this is just 60 ppb, but 60 ppb with, so the SPE cleanup. I can see, so after this SPE cleanup for 60 ppb, so it can achieve, so the same signal to noise ratio, that means the same sensitivity as that for 1 ppm, okay? So without, so that means with the strong contact exchanger cartridge to do the cleanup, that do help to increase the sensitivity, so a lot. That is not just for this pair, you can see, and also for different pairs, right? Okay, yeah, so you can see that's different pairs, that one. Okay, so if we summarize that one, so and this the Helix analytical method for the melamine is quite simple, sensitive, and it's really good for the screening. So, and it's suitable for varietal matrix. So, and also if you're running like say MRM mode and go to ppb level, and still you can see enough sensitivity. And if you want to simultaneously analyze melamine and cyanuric acid, so you have to think about divide into two portions. One goes through the strong contact exchanger, one goes through the strong ion exchanger. And then when you're doing the analysis, you want to do that separately because one need to use ESI positive, the other need to use the ESI negative. Okay, so that's all for here. And now we can go to UPLC part. Okay, so okay, so now it's the UPLC part. So UPLC means ultra performance liquid chromatography, and we already mentioned a little about it. So the main difference between HPLC and UPLC is actually dP, right? So the diameter of the particles, packing materials in a column. So, and instrumentation is very similar to HPLC, and different module added together, pump, then a sampler and UV detector, and can be mass detector. I will look at the HPLC and the UPLC if we do the comparison. So, and then, so the particle diameter of HPLC is about 10, then narrow down to 5, and then even smaller to 3.5 micrometer. And then, so the column normally length is about 4.6 millimeter times 250 millimeter. This is the length, and this is the inner diameter, okay, of the column, or even thinner one, and also shorter one. And the pressure is between handling pressure, normally between 1,000 to 3,000 psi. So for psi is 1 atmosphere equal to about 14.7 psi, right? So if you see something so higher than 3,000, already you feel like it's pretty high, and then you have to think about it. So, and you can do that gradient analysis, and it takes about 45 minutes. But for UPLC, so it's developed in 2004. And for dP, for diameter, we can see that now it decreased to 1.7, so micrometer. And then, so the column can be even shorter. It can be like 50, so millimeter long. And because it's using much smaller particle, and then it's more difficult to push the solvent to go through the column. So that's why you can see it handles, even it has higher performance, and then so it has higher pressure as well. So the typical pressure is between the 2,000 to 14,000 psi. And then the analysis, because it's shorter column, and also the flow rate can be faster, and then so it has the analysis time can be just within 10 minutes, okay? So it can be pretty fast. So this shows the Van Dempster diagram for different diameter. So you can see, and this one says dP equal to 5. And so you can see dP is decreasing. So from 5 to 3.5 to 1.8, 1.7. What we can see is, first, when dp decrease, h decrease, right? Okay, so the plate height decrease, and same time we see mu optimized. So this means mu optimized one actually increase. So, and you can have more optimized flow rate. That means you can achieve same resolution, same calling efficiency using a higher flow rate. That means shorter time, right? And also you can see get flatter and flatter. So here's A, B, C. This part is the influence of C mu, right? Okay, because H equal to A plus B divided by mu. Mu is velocity and C mu. Okay, C mu. And we can see that with decreasing particle diameter, the C, this one get flatter and flatter. So that means the influence of C mu, so this term on H getting lower, this influence. So it's getting lower. Okay. So that means what does it mean? That does mean that because it reduce the effect of the C term on the plate height value. So that means you can run faster separation. You can adopt a faster mu. So while keeping very similar resolutions, calling efficiency. Okay. So this is the point. From that, I already see. So when dp decrease, so it can make so many changes. Now let's go through details. This one. So, right, okay, you can write it down now. So easy to fill in the blank, right? Okay, so when dp decrease, because A turn equal to what? A still remember? 2 lambda dp, right? So A turn decrease. C turn, this is a stationary phase, right? And this is, we also have C moving mobile, stationary phase, static mobile phase, right? CM. So this is CM, M, and CMS, right? Still remember? C turn has stationary phase, mobile phase, and mobile phase has moving mobile phase and static mobile phase. And normally, the mobile phase C is much larger than that from stationary phase. So we'll focus on this two. If I focus on this two, what do you see? I see something in common. I see something in common. Right. So the C mu is proportional to what? So the C mu here actually is proportional to dp squared dm mu, right? Okay. So C mu is related to that one. Okay. So, and we'll use that later on, just that from here, look at. So why? So C mu is proportional to dp divided by dm mu. Okay, so anyway, we can see when dp decrease, C term of course decrease as well. And then so therefore, so the plate height decrease. So because n equal to L divided by H. L is what? Colon, length, right? The colon length. H plate height, right? So when H decrease, N increase, right? Okay, so N is plate number. Remember, plate number is related to resolution. So the resolution is proportional related to the square root of plate number. So if plate number increase, the resolution increase. So this is how everything related to each other. Got it? And so far, I'm too fast. Is that okay? So follow here so far. Okay. So I assume. Okay. Thank you. So good. So that's why we see. So with dp decreased. Let's see. Oops, sorry guys, because of block here. So bit 2 and okay. So and because also we see that because the C term, So with lower, smaller dp and the c mu, that one all decreased, and then that reduced effect of c turn on the h value. So that makes us to be able to run the separation at faster speed. So have with the similar resolution. So and see, because then that's why the smaller the particle size is the true reason for the UPLC has increased linear flow rate and also increased resolution. So why we say linear flow rate? Okay, because actually mu, this one, optimized flow rate, is also related to dp. It equals to, oops, 3dm divided by dp, okay, dp. And also you can see, because now we say c mu is proportional to d, so that's why c mu now is proportional to what? To dp squared divided by dm times mu, right? Which mu is now 3dm divided by dp. If we do the cancel, so that equals to 3dp. So that means, so c mu is proportional, so relate to 3dp. Okay, so and now because a so is proportional equal to 2 lambda dp, and if c mu, this one, is proportional to 3dp, and this one cross out, so dp here, dp here, so that means h is proportional to dp. So when dp increase, h increase. When dp decrease, h decrease, right? Okay, so and so that's why we get this one. And so n is proportional to what? Now n proportional to what? 1 over dp. So that means when dp decrease and then n increase, right? And then so that's why. So resolution now proportional to what? To dp square root, 1 over dp square root. And then so because how about mu? Mu is proportional to what? Mu is proportional to, so 1 over dp. So if dp decreased and then so the velocity increased, right? Okay, so if column length, so it's the same as the plus times form is the same. So and how about the time for analysis? So what is time for analysis here? So time for analysis means length divided by what? Velocity, right? Okay, so and if dp decrease, so if n increase, right? Okay, so sorry, so dp increase, decrease, and mu increase, and then the time decrease. So that means, so with decreased dp, you see how many terms get influenced. You get faster speed here, mu here, right? You see, and also you get shorter analysis time. So then you get faster speed, okay? And then at the same time, so you got increased resolution, dp decreased, resolution increased. Got it? Okay, so far good. So let's move on. Okay. So, and therefore you can see, so it has advantage for speed, resolution, sensitivity. Oh, we didn't mention sensitivity here. Okay, so if column length is unchanged, so n is actually proportional and to the square, so inversely proportional to the square of the what? Peak width. W is peak width. What does it mean? It's like, say, we see that. So if it's more efficient, you can have different kind of peak. This peak, okay, the same amount. But if it's more efficient, it can be narrow and taller, right? Okay, so if increase the sensitivity, that means so the peak width decrease and then the peak height increase and then it gets sharper, it gets taller, and then that means within the certain fixed time you can separate more peaks than before, right? Okay, so okay, so n relate to that one, but also the height of the peak, the height of the peak, sorry, the height, we want a short peak. So the height of the peak is proportional to 1 over W. So what that means? That means the height is proportional to what? N square root. It's proportional to what? 1 over dp, right? Am I right? Okay, so that's it. Okay, so that means if your dp decrease, the height increase by the square root 1. Okay, so that's why it means sensitivity. Okay, so you get high speed, better resolution, and higher sensitivity. And then for an instrument, the UPLC also have a better reproducibility, not for injection, but also for the gradient. And also it has good stability for instrument and so on. And for efficiency, okay, we just mentioned about because N equal to L over H. Okay, because the H is proportional to dp, right? Okay, so that's why we can write H equal to small h dp. Okay, because proportional to that. Small h here is reduced height equivalent to a theoretical plate. And then so that's why you can see written down this way. So and when dp decrease and increase, and resolution is by this way, related to selective factor, related to n number, and increase resolution increase. So the goal is to obtain separation conditions with highest resolution possible. So and then this can be achieved by so increasing n number. But however, so when we have smaller dp, so that causes a big change or impact on what? On pressure. Okay, this pressure drop. You can see the pressure drop gets larger when dp is what? Decrease. Pressure drop increase. So what are all other terms? Find flow resistance factor, linear velocity. Oh, so here is what? Mu. Still remember mu optimized equal to what? 3dm what? dp. Okay, if we put that in, so actually you see that delta p is proportional to what? It's not just proportional to 1 over dp square. It's proportional to column length. Don't miss this one. L means length, column length. Okay, so this one is viscosity. That means if you want to have smaller pressure drop, you want to use less viscous. Okay, so mobile phase with smaller viscosity and proportional to L over dp triplet, right? Okay, not just square. If you put this one in, and then it's delta p actually proportional to L over length over dp triplets. So that means like if dp, if I say if dp decreased by 3 times, what happened? What happened? That means the delta p will increase by how many times? Can you tell me? So how many times? Triplet here, if length is the same, if length is the same, if L is the same. So, okay, so because this triplet here, 3, 3, 3, right? So will increase by 27 times, okay? Increase by 27 times. So if L length keep the same, okay? So you can see. So, and talk about advantage of this sub 2 microgram, this one. So I say the speed. So when the particle diameter drop from 5 to 1.7, 1.7, that is almost dropped by about dropped by 3 times, right? About dropped by 3 times. So 9 times speed, what do I mean? It means like if you want to, if keep, how about I do this way? So how guys say, I say if keep resolution the same, if keep the resolution the same, when dp decreased by 3 times, if we keep the resolution the same, what happens? If we keep the resolution the same, that means you keep n same, unchanged, right? Okay, 1 time. So keep 1 time. So, and that means what? Because n equal to L divided by h. Because h already decreased by how many times? 3 times. Okay, so put it n 1 time. Same. So because h decreased by 3 times, if you want to keep n unchanged, that means what? It means the length. So you have to switch to a column with column length decreased by 3 times. Okay, if column split 3 times, how about mu? Velocity. This one equal to what? Still remember? 3 dm over dp. If dp decreased by 3 times, this one increased by 3 times. Okay, so the time, that means the speed, the time we can use for analysis now equal to L divided by linear velocity. Because now L decreased by 3 times. So, and velocity increased by 3 times. Shorter length, faster speed. So that's why, so the T overall, what happened? Increased by 9, oh, sorry, decreased by, sorry. Hold on. Oh, sorry, guys. Okay, 1 minute. Sorry, guys, I'm back. Okay, so, and then you can see that, so that's why T decreased by 9 times, okay? Decreased by 9 times. So that's the reason when you are changing from 5 micrometer to 1.7 micrometer, so when the dp decreased by 3 times, so, and then, so that's why, so the time can be 9 times, so shorter, so, and then that means faster for analysis. So this one, so it's about 2 times, dp decreased by 2 times, and then so the speed is 4 times. If you keep n unchanged, if you keep the resolution the same, okay? So that's why, and then so, and cm is that one, because cm is, as we mentioned about, equal to what? dp square proportional to dm, right? If you're not here, so if it's dp decreased by 3 times, and cm, that one decreased by 9 times, okay? So, and that means for the same similar effect, you can increase using a much faster speed, okay? And let's see, so as particle size decreases, so, and mu optimized increase, yeah. So this is what we actually already mentioned, right? Okay, so you can see with, because of this relationship, and then so when dp decreased by 3 times, and then so optimized flow rate, mu optimized, this one increased by 3 times. Okay, and if you, and then so of course, because the H also decreased by 3 times. So, and then, so that's why N increased by 3 times. And then, however, if you want to keep N the same, okay, and then, so the only thing for you to do is to use a shorter column. You can, that means you can use a shorter column. You can use a shorter column. So, while keep the N the same, right? Okay, so you can use the 3 times shorter column, and then that makes your analysis time to be shorter by 9 times. So, however, you have to consider pressure drop when dP decrease, because we already mentioned that. So, and optimized flow, this one is actually, I will say, better not to say 1L, okay, keep this LN, consider about L. So, proportion to L over dP 3 times, okay, triple it, okay, and then so that's why, so when the dP decreased by 3 times, so about like say 27 times, but this one, why the reason is just 25, because actually 5 divided by 1.7, so it's equal to 2.94, not really 3, so that's why. So, and 2394, and this one, so triple it, so it's about 25. But however, if you keep N unchanged, if N unchanged, if N the same, so now you have, so column length 3 times shorter, and then so that means, so L 3 times shorter, oops, sorry, and then so you have dP squared here, so which is how many times? So dP triplet, sorry, which is 27 times, right? Okay, so smaller. So that's why overall, so you got 9 times, okay, because it's about 80 because of this one calculated from here. Got it? Okay. So far, any question? Fine with it, because I have increase, decrease, increase, decrease. Yeah, you may get real. Okay, so don't worry. So we go through some real example and we'll do some practice together. Okay. So, and then when we do that practice together, so, and then, so it may be easier for you to understand. So here, let's see. So this is one example. So here, particularly, want you look at this pressure change. Okay. So this is the same column. So, but now if you change the packing material, so diameter from 4.8 to 1.7, so that is about, let's assume that is about 3 times, but actually 4.8 divided by 1.7 is about, so it's about 2.82, okay, 2.82. So, and then we can see now dP decreased by 2.82, and then so therefore N will increase by what? 2.82 times. And then so what happens? And then so what is the resolution? Resolution is proportional to N square root, and then so that will be 2.82 will be 1.7 times larger, okay, increased by 1.7 times. See, seven times. Okay, so and T equal to L divided by mu optimized, because also here the velocity, linear velocity, will also increase. So by how many times? 2.82 times, right? Okay. So, and if we keep the column length unchanged, so because this one increased, T, so will decreased by, so which is, so you see, so T will be decreased by 2.82 times, right? Okay. And then so delta P, delta pressure, P equal to L divided by dp triplet, because now we're using same L unchanged, it's the same. So that means what means the delta P will increase by how many times? By 2.82 triplet times, which is about 22, which is about 22.5 times increased. Okay, so that's why. You see that sensitivity, resolution 1.7, and then so this one, yeah, and then faster the time, about this point faster, right? And then pressure increased by that. And sensitivity, what is sensitivity? Sensitivity is the height, right? Height, which is proportional to 1 over dp square, right? Because dp decreased by about 3 times as square root. That means the height. So actually, so it's kind of increased by that. So it'll be increased by the square root of 2.82. Okay, so if you calculate that, it will be 1.7. In reality, it's this one. Okay, so that is how that works. But from that, you see, because the pressure drop has increased by so many times, 22.5 times, that's a lot. So it increased a lot, right? Okay, so that's just too much. So however, so if you really consider about that one, really consider about it, so the way to do so is then can use a shorter column. So when the part diameter change, can consider about the, because you get enough good resolution, because here now everything well separated, so they look totally fine. Okay, so you see I'm fine with this resolution, and then so by decreasing the particle number, so I can achieve the same resolution with much faster time. So you can see here the time just decreased from 30 minutes to 4 minutes. That is what? That's how, about 9 times, right? About 9 times faster. Okay, so here, this one is if keep the same resolution. Keep n the same. N the same. If we have to keep the n the same, if the dp, how about we just, how about to make it this easier, straightforward, I just say dp decreased by 3 times, okay? And then, so if we keep the n the same, so L 3 times, right? Okay, so then mu optimized, this one increased by 3 times. So that's why T, which is equal to L divided by mu. So that means T will decrease by 3 times 3, 9 times, right? Okay, and then pressure equal to L divided dp triplets, and this one already decreased by 3 times, and this one decreased by how many times? So, and this one decreased by 27 times. So that's why it goes to dp decreased by just like 9 times, right? 9 times. And then so for this one, the sensitivity here. So and so if it's the constant one, because now we are using the constant n, right? So n the constant. So if same, and how we can know the sensitivity? Okay, so and then if the same and the height is no longer so proportional to n square root, is proportional to 1 over L. So that means because L decreased by 3 times, so that means height so increased by 3 times. That means sensitivity increased by 3 times. So this is how it gets this here. Okay, so I hope you follow it. So for any question? Okay. Okay, so then we move on. Okay, so and this is just give you more straightforward so view about if the resolution increased by 1.7. So how does that so influence the pressure drop, that means the difference of pressure will go through the whole column. Understand? So then, I mean, like say, that means that the difference of the pressure. Okay, so that means the pressure drop. Understand? So that's what we call it. Okay, yeah. So it's not really means that the pressure dropped. Okay, it means like say a larger, we say a larger pressure drop, larger difference. Okay, so and then here is resolution 0.4. If we sensitivity resolution increased by 1.7 times, so how does that effect on resolution here? When we see that when your resolution equal to 0.4, actually the two peaks cannot be separated from each other. Well, when it's increased by 1.7 times, so it's about 0.7. So now we can see, so the two peaks can, at least we can see there are two peaks. And for this is what it looks like for the two peaks when the resolution equal to 0.8. Okay, so when it increased by 1.7 times, so because then you can see, and then so at 1.25, the two peaks can already well separated. Okay, so this is the meaning of that. Even like the resolution only increased by 1.7, but when it shows up, so in the chromatogram, so you can see the peak already increased the separation. So we say also of selectivity that increased a lot from, so the two barely separated one to be well separated, or two totally co-eluted one, so and merge one into something like already we can see actually there are two peaks. Okay, so and this is our sensitivity, how we calculate that. We say this is when, so we keep the L the same constant, and then so, and this is sensitivity related to that, because the narrower the peak, the easier they can be separated from each other. And then however, if you assume the same efficiency, that means n the same. If you keep the n the same, and so the peak height in inverse proportional to the length of that. Okay, so the length of that, and then so and for the same efficiency, column length decreased proportion to photo size and decreased by 3 times, and then so, and the sensitivity, which is proportion to 1 over L, and then will increase by 3 times. Okay, so question. So how about you guys do that by yourself? So I give you 2 questions. So first one, given L length, column length remain the same, the particle diameter decreased from 5 micrometer to 1 micrometer. How does that influence the speed, resolution, so efficiency, pressure drop, so optimized linear flow rate, and sensitivity? Okay. So the second one is, given that resolution remain the same, so and for the same change of dp, that means change from 5 micrometer to 1 micrometer, how does that influence the speed, resolution, so efficiency, pressure drop, optimal flow rate, and sensitivity? Okay, so can you guys try that by yourself first? Yeah. Did you get an answer? So anyone want to, for the first question, if L remains the same, so how about the speed. How about resolution? Yeah. So how about everything? So L remain the same when dp decreased by 5 times. Okay, so how about N? How about N first one? So N, do you want to answer the question? So N decrease or increase by how many times? So anyone try to answer the question? How about N? How about you guys just answer N resolution speed? Okay, do you want to answer that question in the chat box? dp decreased by 5 times, and then so N equal to L. Yes, very good, thank you. So increased by 5 times, N increased by 5 times. So how about others? Did you try that by yourself, guys? So that's why that's a point. Yeah, very good, thank you. So, and how about resolution? How about resolution? Can anyone answer the question? The resolution. So increased by how many times? So resolution increase, right? Okay, thank you. So I already see the answer, 2.24. Very good. So 2.24 times. Very good. Okay. And then how about mu optimized, right? It's very easy, right? This one, how about answer this question? Don't be shy. How about the optimal linear flow rate? So increase or decrease? Increase, right? Okay, so this one, I see the answer, increase by 5 times. And then, so that's why. So how about the time? How about the time? Yeah, thank you. So, and then how about the time? Thank you for those answer the question. So T, how about the time? Time then is shorter by 5 times, right? Okay. So how about sensitivity? The 6 noise ratio. So we're talking about looking about the height. So, or how about I wrote it in about 6 to noise ratio, the sensitivity. So which is what? Proportional to what? N square root. And then which is, so means it will increase by how many times? Increase by 2.24 times as well, right? Okay, 2.24 times as well. So, and how about delta P? And because the pressure drop dP, and then so that's why it has what? So will increase by 5 triplet, 1 to 5 times, right? Okay, so did you get the same answer? Did you get the same answer? Yes or no? I guess if you get the same answer, that is good. So very good, very good. Okay, I see some of you already got the same answer, so that is very good. Okay, so and the next one say resolution remains the same. Resolution remains the same. That means what? That means so N is the same, right? Resolution remains the same. N is the same. Okay. So that means if you want to keep but however your dP decrease by 5 times, that means the length you can use a shorter column to remain to have the same resolution, right? To with the resolution not changed, still good. And then you can even use a shorter column. So length decreased by, so 5 times. How about I write this way? So, and, so therefore, but again, so optimized flow rate, this one still 5 times, right? Okay, so, and what happened about the t, the time, so which is the length, so, and divided by the rate, so it decreased by 25 times, okay? And then, so delta p, because your length decreased by 5 times, and so it's just increased by how many times? Increased by 25 times. And then sensitivity now, sig to noise ratio proportional to 1 over L. And then so that will increase by 5 times. Okay. Same answer? Did you guys get same answer? Same answer? Same answer? Yeah, okay. So you see that. So one thing you see, the optimized flow rate doesn't matter. The L remains the same or resolution remains the same. As so once dp decrease how many times, it will increase how many times, right? Okay. So it doesn't matter where you L n. But however, you see delta P pressure drop changed. And also we can see that resolution changed because here n is the same. So resolution, because resolution is the same. So n is the same. It's different. And also the sensitivity need to be calculated in different ways, right? Okay, need to be calculated in different ways. Okay, so how about we take a break here? So that's pretty enough for this period of time. So we take about 5 minutes break and we come back at 20:54. Okay, so how about that? So time to drink some water. Okay, so we can start again. Let's see. Okay. So I hope from this, oops, where's my pen? Okay, it's here. So I hope from this one, so you're already very clear about so the influence about changing DP and how we change, make a smaller particle diameter, and how that can influence the resolution, the sensitivity, speed, and so on. Yeah, before I move on, actually, I need to talk about something very important today. I almost forgot. Oh my God. Oh, too busy. Well, let me show you guys. Yeah, let me see. No, not this one. Hold on. Yeah, hold on. So, let me see what happened here. Yeah, I found this one. 1 minute, huh? Bad. Yeah, see whether I can share it now. Hold on. Okay, so you know that we have oral presentation. So now can you see this one? So can everyone see this Word file? It's PDF file. It's about the oral presentation. Can you? Yeah, okay. Thank you, Haxia. Thank you for the response all the time. So, and you see that one. So for this separation science, we're going to have oral presentation, and it will be the group oral presentation. Okay. So, and this one, so count for about 20 marks of the total marks. Okay. And then, so here I want to just point out the group oral presentation will be held on April 6th. That's the last lecture. We have 3 hours. So we'll do that online. So that is group presentation. That means all the group members got the same mark. Okay, so you got same marks from the oral presentation. And now I'll contribute 20% of the overall assessment. So the group oral presentation will conduct through Zoom. And then so and because we have 40 students, so I will divide you guys into 10 groups, and each group contains 4 students. And for your group presentation, so each group has 12 minutes for the presentation, okay? And we have 3 minutes for Q&A. So that means total 15 minutes. So 15 minutes we do what? So that 15 minutes, so finish the presentation, finish Q&A, and then that means for 1 hour, we can finish 4 groups. And then, so that means in 2.5 hours, we can finish all 10 groups. That means we give some buffer time to it. So in case, so noting some things. So because the presentation is on April 6th, so in case like some of you may have some difficulty to share their documents, share the PPT. So just that one representative from each group to send me your final PPT slides. So all before 5 p.m. on the presentation day. Okay, so just then I also have a record for that one. It's also for grading purpose. And then so the PPT should be used with about total of 18 to 22 slides. I mean, one specific for that one. So here is something guideline about so what you need to you need to include in your presentation. So you can just first slide, just your group information. So including your name and student number and the topic. And then then you use 3 to 4 slides, introduce the significance of the topic. So some background and why we need to do that one. Okay, so why we care about this and then what is the problem. Okay, so and then so you use the 11 to 14 slides to do this comprehensive literature review, so of this kind of analysis of this topic. and then so provide examples. Okay, so provide some discussions here, not just give me all words. No, so you want to make it more interesting. So not really like our teacher notes. So anyways, you would want to introduce picture. Okay, you want to introduce some animation, and also so you want to say, even for some of the case, you give some example, like the case study, like what I gave you guys in the class. That is a very long one, but here I only have 12 minutes, so don't give a very long one. Okay, so that is that one. So, and in the end, you give conclusion and then indicate the future technique, what it can be improved or not. Okay, so this one I already uploaded onto BU e-learning. Now is you can download it. Okay, and another very important thing is like the marks of the presentation. So as I mentioned, given to the whole group. So, and also attach the oral presentation rubrics, and you can look at these rubrics and see how we give marks. And again, I give you guys the right to kind of like give marks to your peer students. Okay, so classmates, and then so both Dr. Wan and myself, so we are like sitting here listening to your presentation.